Well, thanks for the invitation. Thanks for the organizers. And this is joint work with Jess Banks and Nikhil. So today I'm going to tell you about a result in non-asymptotic random matrix theory, which I think is of interest in its own right in the random matrix space. But let me start by telling you a little bit about the motivation for this work. And I want to start the motivation by showing you a picture. So here I took a matrix that went over there, 100 by 100. And then I asked MATLAB, compute the eigenvalues of this matrix. So I did that for A and I did that for A transpose. And I plotted the output in both cases. And as you can see, they're quite different, okay? But the entries of A are real, so the eigenvalues of A and the eigenvalues of A transpose are the same. So one of these, if not the two of them, are quite wrong. So what's going on here? In this case, the conspiracy theory is the correct one. What's happening is that on the one hand, eigenvalues and eigenvectors of non-normal matrices can be very unstable, meaning that if you add tiny perturbations to the matrix, then they change a lot. And on the other hand, computations are not exact. So given that you can only use a finite number of bits to store a real number, if you multiply two real numbers or add them up, you will have an error. You can interpret errors as perturbations. And then if you put the two of them together, well, it turns out that it's very hard to compute accurately eigenvalues and eigenvectors of non-normal matrices. And rigorous, like once you've devised an algorithm that you think works well, rigorously analyzing this algorithm and proving that it works is even harder because like you don't have any control on what these perturbations will do to your matrix. So what I want to tell you about today is about the following random matrix phenomenon, which can be stated as follows. So let A be any matrix, and let Mn be a random matrix that has tiny independent entries, each of which has some absolutely continuous distribution. Then it turns out that with high probability, A plus Mn is going to have stable eigenvalues and stable eigenvectors. And I'm going to quantify this. So what's the relevance in terms of designing numerical linear algebra algorithms? Well, if you have an algorithm, call it Eig, that can find eigenvalues and eigenvectors of your matrix, and you want to diagonalize some matrix A, well, instead of running your algorithm directly on the matrix A, run it on A plus Mn, okay? Since your error is already going to perturb your matrix, well, why not perturb it yourself? Have something that you know has stable properties, and then run the algorithm on that. And then it's much easier to prove guarantees for this algorithm. And moreover, it turns out that in practice, sometimes this gives you a better performance. Okay, so in this talk, I want to tell you what exactly I mean by this main phenomenon that I described there. So give you a precise mathematical statement. I want to tell you what were the main ideas that we used in the analysis of this phenomenon. And I want to mention some related work, especially some exciting recent developments, and not by us, but by other people, and some open questions that I think are important. Okay, are there any questions? Yes.
What happens if you perturb the matrix that you showed us and ask MATLAB to compute the eigenvalues?
Okay, then I think you would get a consistent result, but perhaps not the, well, yeah, it would give you eigenvalues that are different from the original matrix. They would give you a consistent result. And what this ensures is to have a backward error under control. So basically, following this method here tells you, like, allows the algorithm to solve exactly a nearby problem to your original problem, which is called this having some backward accurate algorithm. Numerical analysis. Okay, so yeah, so let me state the main theorem, and for this we need some preliminaries. So assume that A is a diagonalizable matrix, and write its spectral decomposition in this way. So here, lambda I are the eigenvalues of the matrix, vi are the right eigenvectors, and because it's non-normal, it's potentially non-normal, then the right eigenvectors and the left eigenvectors might not be the same. Okay, so that's why we have vi wi star, and normalize in such a way that the inner product between wi and vi is equal to 1. So, okay, and define the eigenvalue condition number of lambda I to be the product of the norms of these two vectors. So note that if you have a normal matrix, then wi and vi are going to be the same. So this condition here is telling you that they have unit norm, and then the eigenvalue condition number is equal to 1. But if these are getting close to orthogonal, in order to achieve something like this, you need to make one of them really large, right? If they're close to orthogonal. And in fact, in the Jordan block case, these are orthogonal. And well, we say that this is an infinite quantity. So this is like a measure of non-normality in some sense. And it relates to perturbation theory in the following sense. So if you have a smooth trajectory in the space of matrices, at every time t, you can take the spectral decomposition. So this gives you some trajectory in the space of eigenvectors and some trajectory in the space of eigenvalues. Then the derivative of this eigenvalue is equal to this. And you can upper bound the magnitude of that by this condition number over here. So this condition number is controlling the rate of change of the eigenvalue when you add a perturbation to the matrix. That's basically what it's doing. And we need another notion, which is that of the minimum eigenvalue gap. So given a matrix A, define gap of A as the minimum distance between two eigenvalues. Okay. And this one is relevant in perturbation theory of eigenvectors in the following sense. So if AT is some smooth trajectory in the space of diagonalizable matrices, then again, you can take at every time t the spectral decomposition. And now the rate of change of the eigenvectors is controlled by this quantity over here. So as you can see in the top, you have the eigenvalue condition numbers. And in the bottom, you have this quantity over here. So if you want stable eigenvectors, one necessary condition is going to have small eigenvalue condition numbers, but you also want a decently sized gap. Okay, so these ones on their own control the stability of eigenvalues. If you also have big gaps, then you have stability of eigenvectors. So what we showed is that if A is some n by n matrix and normalize it so that it has norm at most 1, and Mn is a random matrix with independent entries that have an absolutely continuous distribution. So if A was real, then take your randomness to be real. If A was complex, then take this density to be a density in the complex plane. Assume that the density is upper bounded by some constant C, meaning that your random variable doesn't concentrate a lot around some point, and assume that it has a finite Ford moment. So we showed that for any gamma bigger than 0, with high probability, this quantity over here, the sum of the squares of the eigenvalue condition numbers, is going to be controlled by a polynomial in the dimension and in the inverse of gamma. Okay. So when you do analysis of how these machine errors are affecting your algorithm, these condition numbers usually go under the log because you want to kind of like how many bits of precision are you losing when you do these things. So having a polynomial control is enough in that sense. And we also showed that the gap is large in the sense that it's bigger than some moderate polynomial in n inverse and gamma. Are there any questions about these results? Oh. So let me tell you at a high level what proof technique is. So when you work with non-normal random matrices, it's kind of hard to understand them directly. So one common technique is to change the problem of understanding the random matrix Xn to understanding a family of random matrices that are now Hermitian. But now for every Z in the complex plane, you're going to have a random matrix, namely the one that appears over there. So it is easier in the sense that now you're working with Hermitian matrices. It is harder because now you have to analyze like an infinite number of matrices. Hopefully your analysis will be kind of like uniform in Z, but sometimes it depends on Z and then it becomes more complicated. So in our case, specifically, what we do is reduce the problem of obtaining tail bounds for these condition numbers and gaps to the problem of obtaining tail bounds for these singular values of the matrices of the form C minus A minus gamma Mn. And by the way, during in this talk, I'm going to denote the singular values in this way. So sigma n is always going to be the smallest, and sigma 1 is always going to be the largest. And okay, so once you've reduced the problem to obtaining tail bounds for the singular values, well, the step 2 is to actually proving those tail bounds. Okay, so this kind of like decouples the structure of the proof. And just to give you an idea of what tail bounds for singular values look like, well, there's these very nice results of Sharek and Schniadi that when you combine them, say the following. So if Gn is a normalized Ginevre matrix, that means that you take some matrix and the entries are independent Gaussians of variance 1 over n, and gamma is bigger than 0, then the kth smallest singular value of this random matrix over here is going to be of order a constant k over n, and the probability that it goes below that multiplicatively by epsilon is going to be controlled by this quantity here, epsilon over gamma to the k squared. So for example, when k is equal to 1, you have the smallest singular value, and then you have a linear decay in epsilon. And in the complex case, so if you use complex Ginevre, you have more or less, well, you have almost the same thing, but now you get a 2 here, okay? And the reason for this is that, for example, if you're looking at the smallest singular value is the distance to the set, so it's the distance of your matrix to the set of singular matrices, of non-invertible matrices. So in some sense, asking that this is below epsilon is taking an epsilon blow up of the space of singular matrices and measuring how big that is. And because the codimension of singular matrices is equal to 1 in the real case and equal to 2, the real codimension is equal to 2 in the complex case, then here you're computing a length and here you're computing an area, and that's why you get 1 and 2. So that's kind of like the equation behind this. And you can do the same for the variety of matrices of rank n minus k. So part of what we did is we obtained results with the same epsilon dependence than the ones you see over here, but our results hold for random matrices like the ones I told you before. So you only need density for their distribution. They don't have big options. And this wasn't very surprising because there are many techniques to do this. But what was essentially new when we did this, and this is hard, is that our tail bounds work in the real case. So when Mn is real, and for Z in the complex plane outside of the real line. So here, this matrix doesn't have purely real entries, it has a bit of complexity inside it. So this like intuition of the codimension that I told you is a bit strange here because you do have a bit of complexity, but this deterministic, it's kind of like very isolated. And in this case, this gets replaced by something that also depends on the imaginary part of Z. And what I learned from this project is that the real world is challenging and full of surprises. So let me show you another picture. Here, I took the eigenvalues, the empirical distribution of a real Geneva matrix, and here of a complex one. So they both converge to the circle, the uniform measure in the circle in the limit, but note that this one exhibits strange features. So for one, look at the real line. So it has a lot of real eigenvalues. And moreover, it seems to have some diminished density around the real line. So that's due to some like repulsion effect around the real line. And this is related to this thing that I was telling you, that if you take a Z here, the behavior of the smallest singular values will change depending on where exactly in the complex plane you are. So really proving the theorem I told you about in the real case is much harder. Okay, any questions so far?
So in your pictures,
Yes.
the limit densities are the same.
Yes, the limiting densities are the same. So the number of eigenvalues on the real line are ordered square root n. So in the limit, it disappears. Yeah. Okay. Okay, so now let me tell you how this hermetization argument goes for the gap. So remember, what we want to show is that with high probability, the gap of A plus gamma Mn is lower bounded by some polynomial in an inverse and gamma. Okay, so the step one is to remember a purely linear algebra fact. So if you have X, some n by n matrix, and sigma 1 up to sigma n and lambda 1 up to lambda n are the singular values and eigenvalues respectively, then the product of the smallest k singular values is always upper bounded by the product of the magnitudes of the smallest k eigenvalues. That's just a very old linear algebra fact. And this is going to allow us to access small gaps around a given point. So fix some complex number Z and define X and Z to be this random matrix here. So Z minus A minus gamma Mn. And note that if the random matrix you're interested in has at least two eigenvalues in the disk centered at Z of radius R, then when you shift your matrix to Z, all of your spectrum shifts, and now those two eigenvalues will be moved to be around 0. Okay, so if you had two eigenvalues in the disk centered at Z of radius R, now you'll have two eigenvalues centered at 0, in the disk centered at 0 of radius R. And because of this linear algebra fact that I told you about, now the product of the smallest two singular values will be smaller than the product of the smallest two eigenvalues, and this is controlled by R squared because of this. Okay, so that's very simple. But what we've done with this is that we've witnessed the event that there's two eigenvalues around Z by saying that the product of the smallest two singular values of your random matrix is small. So then you get that this probability is controlled by this probability over here. And this is kind of going in the direction we wanted, right? So we want to reduce the problem of obtaining tail bounds for gaps to obtaining tail bounds for singular values. Okay. So that allowed us to work around a point Z, but we want like, we want a result about gaps anywhere, not just around Z. So what do? We take an epsilon net, okay? And to do this for each complex, number Z and R, defined EZR to be the event that the random matrix has at least two eigenvalues in the disk. So let's see, radius R. And what I said, the probability of this event is controlled by the probability of this event over here. And I promised that we were going to prove results like those of Sharek and Schniadi. So that will give you, if you plug in these like tail bounds, this will give you some polynomial control on the probability of that event. So the control is a polynomial in R, N, and gamma inverse. Okay. Moreover, we assume that A has normal pose 1. Yes.
Why do you have poly 1? Still meaning that?
Oh, because I'm going to write another expression that also says poly 1. So just to show that it's the same polynomial afterwards. Yeah, maybe that's not great notation. I wanted to emphasize that it's a polynomial. Yeah. Okay. And the fourth moment condition on the entries of the random matrix ensures that the norm of the random matrix is O of square root n with overwhelming probability. So when gamma is small, which is the case in which we're interested in, because we want to analyze small perturbations of a given matrix, we'll have that this norm over here is upper bounded by 2 with very high probability. So what does that imply? Well, that all of the action of the eigenvalues of this random matrix is happening inside the disk of centered at 0 and of radius 2. Okay. So then what we do is we take some epsilon net on that disk, and we want to study the probability that the gap is smaller than some parameter. Well, if you have an epsilon net there, in that disk, well, two things can happen. So one of them is that something very strange happened and you just got a big norm, okay? So that's going to have some very small probability. And the complementary event is that all of your eigenvalues are inside the disk, in which case this small gap is going to be witnessed by one point in the net. Okay, so there's going to be a point in the net around which there's two eigenvalues, and then you'll have that this event EZR happens for some Z in the net and for R equals epsilon. Okay, so let's now overbound this probability. So you do a union bound, right? So then you get the size of the net times this polynomial upper bound. The size of the net is of order epsilon to the -2 because we're in the plane, and so then you have to pray for this polynomial to subdue the effect of this net. And yeah, if you do the computations, turns out that the epsilon dependence here is better than epsilon squared. So at the end, you get something that decays with epsilon. Okay. Any questions about this proof? Okay, cool. So that's how you control gaps. How you control the eigenvalue condition numbers is a bit more, just slightly more sophisticated, but it's also pretty simple, and I'll show you how. Okay, so we want to prove this, and these arguments that I'm going to show you first appeared in another paper, and it's so since I'm not in that paper, I'm allowed to say that it's a very beautiful argument. That's what I'm going to show you right now. But it only works for complex, and I'll tell you why, and then I'll tell you what we have to do in the real case. Okay, so a key element of this argument is the notion of pseudospectrum, and this is very important in perturbation theory. So let me spend a bit of time on this concept. So if A is an n by n matrix and epsilon is a number greater than 1, the epsilon pseudospectrum of A is defined as the region in the complex plane that contains those Z for which the resolvent, the norm of the resolvent is at least 1 over epsilon. So you want those complex numbers Z such that Z minus A is almost non-invertible. When epsilon is 0, this is infinity, and you're just asking for which Z's is Z minus A not invertible. Well, those are the eigenvalues. Okay, so this is some like generalized notion of spectrum. To give you some intuition, one can show, and this is not hard, that the epsilon pseudospectrum of a matrix is the union of the spectra of the matrices of the form A plus E, where E has norm less or equal than epsilon. So it's running over all E's, less or equal to epsilon. And in this context of numerical linear algebra, well, you can think of the epsilon pseudospectrum as the region where you can find eigenvalues if you perturb your matrix by epsilon. Okay, okay, so this fact we will use. For small epsilon, so for big epsilon, these regions take all sorts of shapes, but as epsilon goes to 0, it starts looking like a union of disks around the eigenvalues, and the radii of those disks is of order epsilon times the condition number of the eigenvalue plus something of smaller order. And if you
so you're saying distinct eigenvalues, and the condition, the kappa is like 1, or sorry, because kappa was related to the size of the Jordan block, right?
No, so this is related to how sensitive the eigenvalue is under perturbations. So in the case of the Jordan block, this is infinity. In the case of normal matrices, this is 1. And then actually in the case of normal matrices, using the functional calculus, you can show that these two are equal and that Ri is just epsilon. So in some sense, if your eigenvalues are very sensitive under perturbations, this region will be very large. And that's what this is saying. And that's related to this in that sensitivity is quantified by condition numbers. Okay. So if A has distinct eigenvalues, because of this, if you compute the area of this pseudospectrum, well, it's going to be roughly epsilon squared times kappa lambda I squared times pi. So each of those disks will have that area. If you add that up and divide by epsilon squared and take epsilon to 0, you'll have that this limit, the expression of the limit of this expression is going to be pi sum over the eigenvalues inside your region B and the sums of the eigenvalue condition numbers. Okay, any questions about this notion? Okay, cool. So this is what we were saying. The normal case, so this is a plot of the pseudospectrum for 2 values of epsilon. In the normal case, you just get concentric circles. In the non-normal case, well, first you don't have circles necessarily, but also there's usually this point where if epsilon is large enough, then these things merge, and at that point, it's kind of like the size of the pseudospectrum blows up. Okay, so how do we reduce the problem of obtaining a tail bound for this quantity to obtaining a tail bound for the singular values? So that's what I'm going to tell you about now. So what you do is you fix some open set in the complex plane and recall this thing that was there 2 slides ago. This expression is going to be important. And note that for fixed epsilon greater than 0, well, I put volume, but it's really an area, right? So you want to know what's the area of this region over here. Well, integrate over B, the indicator that your Z is inside that region. Now, by definition, Z is inside the region if the norm of the resolvent is at least epsilon inverse. Okay, so here I haven't done anything interesting. Now, it's a well-known fact that the norm of the inverse of a matrix is 1 over the smallest singular value of the matrix. So here I had a greater or equal than. So if you multiply this way, then now you have the region of the Z such that the smallest singular value is upper bounded function epsilon. If you do Fubini, then you have the expectation of an indicator, which is just the probability of an event. And now this is exactly what you wanted, right? So this is saying what's the probability that your smallest singular value is less or equal than some epsilon. So now, by this result of Sharek and Schneali that I showed you, regardless if you use complex universe perturbations, so if Mn is like Jn, then it doesn't matter what C or A you have. This has an upper bound regardless of these two parameters, which is this one here. And now we're integrating, but over dz and this is some constant. So we're pretty much done. So let me put this thing that we just deduced over there. So if you divide by epsilon squared, both sides, and take epsilon to go to 0, then the left side is precisely going to be the thing that's separated above. And you get that this volume that you had over here, now you've divided by epsilon squared, upper bounds this quantity over here. That quantity converges to the sum of the eigenvalue condition numbers. And with this, you've controlled the expectation of the sum of the squares of the eigenvalue condition numbers. Once you do this, you can do Markov or whatever you want to get some tail bounds on this quantity over here. Okay, so that's this proof. Are there any questions? This. Okay. So I want you to note that it was crucial that I should have put something at the end of this slide. It was crucial that the upper bound on this decayed as epsilon squared, because that's what allowed us to later divide by epsilon squared and use the expression that appears at the top. Okay. If you don't have epsilon squared, you're screwed in this approach. And remember that, oh yes.
So is the n squared on the left-hand side reasonable?
Oh yes, it is reasonable in the sense that it is optimal. Yeah, it is optimal, and it's also reasonable because we only want polynomial bounds. So any moderate polynomial in n, gamma, and eps, and yeah, in n and gamma at the end is going to be okay.
Because the sum, right? The sum on the right that has the most n terms, right?
Yes, and each one of these is yeah, exactly. So you can show that for the Ginevra, this gives the correct answer. So if A is 0 and gamma is 1. Yeah, actually the question about what this is for real Ginevra was open until maybe 2 years ago. So real Ginevra is much harder than complex Ginevra. So this gives you the correct answer in complex Ginevra, but in real Ginevra, that's a different story. Okay, so the two results I told you are if you slightly perturb a matrix by a random matrix, then you obtain something that has large caps and small eigenvalue condition numbers. We can rephrase this in terms of the pseudo spectrum. So here's a matrix that's kind of like ill-conditioned. And this is the pseudo spectrum. So it has all of its eigenvalues in one point, and its pseudo spectrum at 3 different scales looks like that. If you slightly perturb it, then these eigenvalues just go to different places. And now note that, for example, the orange scale didn't change much in the two cases, But for small scales, like the green one here you had a huge region. Now you have a pretty small one, which means that small perturbations, like perturbations at this scale for this matrix, will just keep the eigenvalues where they are. Okay, that's what one is when diagonalization algorithms. Okay, so those were like the two main ingredients. And as I told you, the technical input is to have a tail band for the singular values. Yes.
So you didn't tell us anything about the non-complex Genebra case, but y'all established a result.
So Erdős wrote a paper with the optimal bound. What we have is the for the real Genebra case keeps something, but it's not optimal.
But you're asserting the results you have hold for all matrices.
Yes.
Those are all perturbations, sorry, with independent entries. And so that means then that if you want to pass from the tail bounds to the control on the conditioning, you need result for other types of matrices.
Yes.
And so y'all managed to do that.
Yeah. I'm about to tell you about singular value bounds that we obtained for the non-Genebra matrix, and for the and also the results on the tail bounds for the eigenvalue condition numbers and gaps is also correct.
Okay, so that was sorry. So maybe that was a connection I missed. Okay.
Yeah. Okay. So yeah. So this is something I already showed. So I just want you to remember how the epsilon dependencies go in this case of Genebra. And as I said, the challenging case is when you have A and Gn real, but you're shifting it by a complex number C. That's not real. What's the correct dependence? So Gay has some really beautiful work on this. And he showed that if the entries of Mn are mean zero, so kind of like in the case where A is zero and their IID, then this tail is upper bounded by epsilon squared, so it has the same dependence as here. But then you have to divide by the size of the imaginary part of Z. So this deteriorates as Z goes to the real line. And in the real line, you shouldn't expect to have epsilon squared. You actually have epsilon. And he had this extra term over here. So now remember in the hermetization argument for the eigenvalue condition numbers, we had to take epsilon to zero to use this fact that the area of the pseudo spectrum when epsilon goes to zero tells you something about the eigenvalue condition numbers. If you have this extra term, you can't take epsilon to zero. And this term is kind of inherent to his proof because he kind of witnessed the smallest singular value by looking at how much the norm of vectors on the sphere shrank when you apply the matrix. And there's some vectors he doesn't know how to handle. And then if you remove this region, then you're fine, but you pay this over here. So with the same proof technique, you can't get something that goes to zero.
So does this work for the non-bounded density? With discrete random variables too? Because right, if it's discrete, you would have that term no matter what, right?
Yeah. If it's discrete, then this is inherent. Yeah, exactly. You can only hope to eliminate this when you have some absolutely continuous density. Something that's great about his approach is that you can have Bernoullis and you still have that result. Yeah. Okay. So what we showed is that if you have some real random matrix with norm at most 1, and you have some Z that also has most 1, then if your entries are sub-Gaussian, so this will allow you to have some control on the norm of Mn, and K is not too large, so smaller than square root n. Then the K smallest singular value, oops, this is terrible. Here there should be a less or equal than epsilon, okay? Is upper bounded by this over here. So we have the same dependence as okay. And for the k small singular values, then you get to exponentiate everything to the k squared. And this is some polynomial in this. So when you do the hermitization argument for the eigenvalue condition numbers, remember we had to do some tail bound for z in the complex plane. Our bound deteriorates as one gets closer to the real line. So what you do is you say, like, because the entries of the matrix are real, then its eigenvalues come in conjugate pairs. So if you have an eigenvalue that's not real and has a small imaginary part, then its conjugate pair would be very close to it. But we proved that there's no small gaps with high probability. So the fact that there's no small gaps and the entries are real tells you that there's some forbidden region where eigenvalues with high probability are only allowed to be purely real. And then what you do is you do this hermitization argument, you integrate over z. Here you have a decay of epsilon squared because you're away from the real line. Here you don't have anything. And on the real line, you have a decay of epsilon, not epsilon squared, but that's fine because you're integrating over a line, not over. So that's more or less how. Okay, so just to conclude, let me tell you about what's been done in this space. So there's this paper from 2005 of Armentano et al., where they got similar results for the complex universe case. So they didn't work with eigenvalue condition numbers or with gaps, but they work with other quantities that also control kind of like sensitivity under perturbation. And their proof requires the coarea formula, which is some formula for integrating and calculating these quantities. And that's very, that really requires you to have like the Gaussian measure. So it only applies to the complex universe case. This nice argument of hermitization of eigenvalue condition numbers I showed you is from this paper over here. And if you work a bit more, so I showed you the proof for complex universe, but really you can get it for complex random perturbations if you want to. Okay, and the proofs, the results that I explained today also appear in a paper of 2020. We uploaded to the archive the same day. So yeah, unfortunately, we solved the same problem. They have essentially different proofs. They're very elegant. They're less methodical, so they can only handle the smallest two singular values because that's what they cared about. But their proof really doesn't extend to the k smallest singular values. So that's a difference. And this is the things I was mentioning of Erdos. So they obtained optimal results for the expectation of eigenvalue condition numbers in the case of real Geneva, and like a month ago or something, Erdos and G obtained kind of like what I showed you, but in the asymptotic regime as n goes to infinity with optimal bounds. Okay, but it's not non-asymptotic. So that's an important difference. They also get some Wegner estimates, which basically tell you that if you take some small region in the complex plane, the number of eigenvalues you'll see there is what it should be. But they do not have control on the minimum eigenvalue gap. So that's okay. And just to end, let me tell you a couple of open problems. So in numerical linear algebra, oftentimes algorithms are designed to exploit the structure of the matrix you care about. Right? So then if you had a matrix with a nice structure and you add a random perturbation, like the one like IID entries, then you might just mess up that nice structure that you could have exploited before. So I think maybe the most relevant open problem in this space is obtain tail bounds for the eigenvalue condition numbers and minimum eigenvalue gaps. of random perturbations of a structured matrix, where now your perturbation has the same type of structure. So for example, if A is sparse, you want to show that if you add a sparse random perturbation, with high probability, you have some controlled eigenvalue condition numbers and minimum eigenvalue gaps. That's very hard. I don't know how to do it because getting tail bands for small singular values of sparse random matrices is a hard problem. And I guess there's these others. Just to give examples, if your matrix is Toplitz's, you would like to add a Toplitz's random matrix. If it's Hessenberg, you would like to add a Hessenberg random perturbation. And the other question that I have is that, yeah, the current results on GAP are, I mean, they work for what we wanted, but they're far from optimal. We don't know what an optimal result for GAP would be. And there's something interesting, like this net argument that I showed you requires the norm of Mn to be bounded with high probability, because that way you can put a net on some bounded region. But you shouldn't need that the norm of this is bounded. Kind of like if the norm is bigger, it's even better to make the gap large. So some conceptual thing that I really don't understand why it's okay.